Hey y'all, today we are going to talk more about, you guessed it, confidence intervals. Today we're going to talk about means. A couple things that we're interested in when we take samples is we're interested in finding proportions of people, proportions of things. And another thing we're interested in is means, trying to find an average. Um, and so we're going to focus on that today. It's going to be similar to the proportions. Um, the basic idea is the same. We're going to change a little bit because we're talking about means. So a standard error is going to change a little bit. Our function hierarchy calculator is going to change, but still same conceptual ideas. So I told you we would have another letter eventually, and that letter is T. So we have been doing Z intervals. When we switch to means, we're talking about T intervals. Um, It's called a T because when we do the distribution of sample means, the curve changes based on the sample size. And you can see down here, if you want to, you can go in the book and read about that. But the big deal is that the curve changes based on the sample size. So the larger our sample gets, the closer our curve will look like the standard normal curve. So a smaller sample means a different curve. In fact, I think this solid one is a smaller degrees of freedom. So we'll get closer and closer to the normal curve the bigger our sample gets. And I mentioned that word degrees of freedom there. Degrees of freedom is just our sample size minus 1. So when we're calculating this T star, it's not a Z star anymore. You can see that N minus 1 subscript. Uh, that's the degrees of freedom. In the calculator, it will ask us for the degrees of freedom df. And we'll have to do our sample size minus 1. And then we have a different standard error. We take our standard deviation from our sample, S, and divide by the square root of the sample size. I want to point out, too, that in the book, they use Y bar for a sample mean where we will use X bar in the calculator, X bar when I talk about it. So just know that in the book they use Y, we're going to use X. I don't want you to be confused. Uh, they mean the same thing, sample mean. Of course, we need to satisfy assumptions and conditions. These assumptions and conditions are going to look very similar. We always need a random sample. We always need independence. We either need to know for a fact that our individuals in our samples are independent, or we need to know that we've sampled less than 10% of the population. And we need to know that a normal model is appropriate. When we're doing proportions, we check that a normal model is appropriate by doing n times p hat, n times q hat, making sure those are greater than or equal to 10. In our first lesson of this unit, when we talked about distribution of sample means, we need to make sure a normal model was appropriate, and we said a sample size of greater than or equal to 30 is usually good, and that still applies. However, if we have a sample size that's smaller, what we want to do is we want to go look at the distribution of our sample, and if that sample is approximately symmetric and normal, then we can still proceed. If our sample is symmetric and approximately normal, then the sample size won't matter so much. If we have a large sample, then we can deal with some skewedness in our sample distribution, just as long as it's not exceptionally skewed. So you're going to want to look at the distribution of the sample. Either you need to be given the data or you need to be given a histogram. And what we can't have is a huge amount of skewness, especially if our sample is small. It seems like a bit of a gray area. It is, but you want to do is check out the distribution of the sample. So take a minute, read this about salmon farming, and then we'll talk about creating a confidence interval for the mean concentration of this Murex. So not all salmon is wild caught. Sometimes they farm salmon, which means they grow salmon to send to grocery stores and restaurants and put on your plate. And so they are checking to make sure that there are no contaminants, or at least the contaminants are within a certain safe threshold. And one of the things they're interested in is this insecticide Mirex. And so uh, we need, before we construct a confidence interval, we need to make sure that our assumptions and conditions are met. Uh, it doesn't say in here that we have a random sample, so we need to assume that it's random. We can assume. Or we can assume that these 150 salmon are representative of all farm salmon. It looks like they went to different farms. We need independence. Uh, I would say that 150 is less than 10% of all farm salmon. And then we need to make sure our sample size is large enough and our sample distribution is a good shape. 150 is a good size sample. And if you look at the distribution, this is the distribution of the concentration of Mirex in the sample. So the data on this histogram are the individual salmon that they sampled, the 150 salmon, and their concentration of Mirex. So we're not looking normal here, but we're not really looking too skewed. It's okay. And our sample size is large, so we're going to say that a normal model will be appropriate, and so we can construct a confidence interval. Um, we can construct this confidence interval using the interval up here, or we can use the calculator. I lean more on the side of using the calculator. You need to understand how to find the standard error. You need to understand how to find a t-star. I'll show you that. You need to understand what this confidence interval means, and then we can go ahead and we can find it using our calculator. So let's first talk about finding a t-star. Um, I can do second vars. When we wanted to find a z-star, we did the inverse normal. We're saying, hey, what is z that cuts off, in this case, 95% in the middle of our area of a normal curve? Well, you can see right below that is inverse t, and that's going to be what we're going to choose. And so each number of degrees of freedom has a different t-curve. So there's all these different t-curves. So we need to tell it, first of all, the area we're looking for. This is where it gets a little tricky. We want the area in the middle. And so if I'm thinking about a curve, there's going to be a t-star on the right, and then there's going to be a t-star on the left that's the same but negative, and we want 95% of our area in the middle. This is symmetric, so each tail is going to contain the same amount of area, so each tail here is going to contain 2.5%. So to the left of the t-star we're looking for is 97.5% of our area. There's no option here to click center, so we need to tell it the area to the left of the number we're looking for. So in this case, we need to do 0.975. If you need more clarification on that, please do ask. I know that it can be a little confusing. Degrees of freedom is our sample size minus 1. Our sample size is 150. We subtract 1, and we say we have 149 degrees of freedom. And it's going to give us a t-star. 1.976, so 1.98. When we calculated a z-star for 95%, I'll do that quick. Inverse normal. You can say 0.95 and choose center. I have to say 0.975. I get 1.96. So you can see these are very close, but they're not exactly the same. If our sample size got larger, this t-star value would start getting closer and closer to being the same as this z-star value. So that's why we have to make sure we use the right thing. If you're using the calculator function to calculate the confidence interval, it'll calculate the t-star for you. Sometimes you need to calculate it on your own, so you need to know this inverse t exists. So calculating the actual confidence interval in the calculator, we're going to say stat tests. And it's going to be choice 8 t interval. And we have a couple options. If we're given the data, we can put the data in a list and we can just tell it which list we used. We don't have a list, so we're going to choose stats, and we are going to use the data we have. So we have the mean. It is 0.0913. Sorry. The standard deviation from our sample is 0.0495. We have to calculate the standard deviation for a distribution of sample means. So I'm going to do that, and then I'll chat about it. We have to use that standard error formula, the sample standard deviation divided by the square root of the sample size. When we use that, we get 0.004. Easily the simplest little mistake that you can make that will totally change your answer is just using the standard deviation given to you. This is the standard deviation for our sample. We need the standard deviation for the distribution of sample means, and that's 0.004. So we're going to put that in here. We're going to tell it our sample size is 150. Our confidence level is 0.95. And we can calculate. And we're going to get a confidence interval. So we have our confidence interval. We want to interpret it always. We always want to justify that we can do this, calculate the interval, and then interpret the interval. So we always have to make sure we hit the key elements of our interpretation. What confidence level are you using? What is the parameter of interest? In this case, it's one mean. What is the context? We're talking about the level of this insecticide Mirex in farmed salmon. And then we want to state our interval. Remember that quantitative data always has a unit, and so we should use the units, parts per million. So we're 95% confident the mean level of Mirex in farmed salmon is between 0.09065 parts per million and 0.09195 parts per million. Make sure we're hitting those 4 elements of our interpretation. So again, some of the key differences here for a confidence interval for means is that we are now using that t-star with the degrees of freedom, the sample size -1, instead of a z-star. Of course, we have a mean from our sample instead of a proportion. And we have a different way to calculate our standard error. So when we're constructing this confidence interval, we want to make sure we use this standard error. This is on the formula sheet that you get for tests and for the AP. So make sure that when you're doing a confidence interval, or we're talking about a distribution of sample means, that we use this standard error and not just the standard deviation that we are given in the problem. This standard deviation in our problem comes from our one sample. This standard deviation 0.004 represents this the distribution of sample means. Stick with the rest of this video, because there's another problem that I'm going to scroll down to. I'm going to ask you some questions about. If you're having a hard time seeing it on the screen, it's posted on Canvas. So please do answer the questions. If you have questions, as always, feel free to ask, and make sure you do some practice.